So in this video, we're going to look at the integrals of exponential function. Here are the rules. The integral of e to the u du is equal to e to the u plus c, where c is the integration constant, which we get whenever we take a indefinite integral. So kind of like the derivative of an exponential function, we get back that same function. So when we take the integral of e to the u, we get back e to the u, except now we have to have that plus c. And if it's a base other than e, so if it's base b, where b is a positive number that is not equal to 1, then the integral is that same b to the u divided now by the ln of that base plus our integration constant c. So let's take a look at some examples. First example we'll look at is the integral of 2 to the x dx. So this is a integral where our base is 2. So taking the integral, the result will be our exponential function 2 to the x divided by the ln of our base, 2, plus the integration constant c. And that's all there is to that one. So let's look at another one. Now let's say we had the integral of 3 times 2 to the x dx. So we have this additional multiplication by 3. For this, we can use the fact that we have that constant multiplier of 3, and the rules say that that 3 can come outside of the integral and become 3 times the integral of 2 to the x dx. So now we just have 3 times that integral, which is the same integral that we had above. So it will be 3 times 2 to the x over ln of 2 plus c. So if we wanted to, we could write that as 3 times 2 to the x over ln of 2 plus c. So let's look at another example. So now let's say we have the integral of e to the x plus 3x squared. So in this one we have a couple of terms. We have e to the x and 3x squared. So remember that the rules for integration tell us that we can take the integral of each of these separately. We wouldn't necessarily have to write it like this. I'm just writing it like this just to reinforce the rules of integration. So we can think of this as the integral of e to the x dx plus the integral of 3x squared dx. And again, we can do this because we have two terms that are adding. If this was a multiplication, then we'd be looking at something much different. So the integral of e to the x, that's just e to the x, plus the integral of 3x squared, so that'd be 3, then the integral of x squared is going to be 1 over 3 times x to the 3. So remember that we add 1 to our exponent and divide by that same new exponent. And then we'd have plus c. And we only have one of the plus c's because really what's happening is we'd get a plus c from the first integral, a plus c from the second integral, but they're just constants. So they would add together to make a third constant, which is this constant c. So the result of the integration, e to the x plus these 3's divide out, so plus x cubed plus c. And that's our final answer. Let's look at another one, the integral of e to the 5x dx. So now instead of just having a single variable in the exponent, now we have a 5 multiplying that exponent. So this is an example of where we would use substitution. And we wouldn't really need to use substitution on this. We could kind of do this quickly without it, but I'm going to use substitution. So we're going to say that we're going to let u equal the 5 to the x. And then we're going to take the derivative of that. So we're going to take the derivative and say du dx then is equal to 5. And what we can then do is we can replace this dx and we're going to replace the 5x, but we also want to replace the dx. So we can think of this as the integral of e to the u, but now we have u as our variable, so we want to be integrating with respect to u. So we need to replace this dx with a du term. So we're going to take this du dx and rearrange it to say, well, this du is actually equal to 5 dx or dividing both sides by 5, du over 5 is equal to dx. So now what we can do is we can say that dx is equal to du over 5. So we're going to have e to the u times du over 5. And kind of like the constants that we've seen before, this 5 is a constant divisor. So we could bring that out in front and say that this is 1 over 5 times the integral of e to the u du. And now that we have the integral of e to the u du, well, that's the rule that we started off with. So the integral of this will be 1 over 5 e to the u plus c. But because we started out with an x, we need to finish with an x. So we'd go back and we'd replace that u with 5x. So our final answer would be 1 over 5 e to the 5x plus our constant c. And we don't need to divide the constant c by 5 because, again, it's a constant, and dividing it by 5 would just make a new constant, which would just become a new c. So we can just leave it at this c. So that would be our final answer. Let's look at another one. Now we have the integral of 5 to the exponent 1 minus 4x. So again, we have not just an x in the variable, in the exponent, not just a single variable, but now multiple terms. So in the last one we had just a single term with a multiplier. Now we have two terms, but our approach is going to be the same. We're going to treat that 1 minus 4x as being u, so we're going to let u equal 1 minus 4x. So that means we're going to have the integral of 5 to the u, but again we need to deal with the dx. So we need to take the derivative of u equals 1 minus 4x, so du by dx will equal the derivative of 1 minus 4x, which is negative 4. And similarly, we're going to rearrange this to isolate to solve for the dx. So du is equal to negative 4 dx. Divide both sides by the negative 4, and we get du over negative 4 equals dx. So making that replacement in our integral, we get 5u times du over negative 4. And similarly, that negative 4, we can bring that out in front of the integral, and we could think of this as 1 over, or negative 1 over, 4 times the integral of 5 to the u du. So at this point we can take the integral. This is just an integral of the form b to the u, where b is equal to 5. So the negative 1/4, that's a constant multiplier. It will keep on multiplying. It's going to multiply the integral of 5u, which is 5 to the u, divided by the ln of 5, plus our integration constant c. And again, like the previous example, we don't want to leave the integral in terms of u. We started off with the function in terms of x, so we should finish in terms of x. So our result would be negative 5 to the exponent 1 minus 4x over 4 times the ln of 5 plus c. And that would be our final answer. So let's look at another example. So now let's say we have 2x times e to the x squared dx. So we don't have a rule for dealing with multiplication of functions, because we have a 2x times e to the x squared. If we were taking the derivative, we'd have the product rule. And in integration, there is an equivalent to the product rule, but we haven't looked at it yet. But fortunately, if you look at that 2x, it just happens to be the the derivative of our exponent, the x squared. So we can kind of do that same process that we did in the previous one, of saying, well, we know the rule for integrating e to the u, but we have something other than a u in there. We have an x squared, so it's not just a single variable. So let's make it a single variable by letting u equal x squared, and then taking the derivative of that And when we take the derivative of that, we get 2x. So that 2x, well, that happens to align pretty well with this 2x out in front of our e to the x squared. So what we could do, if we think about this integral as e to the x squared times 2x dx, so just taking that multiplication of the 2x times e to the x squared and rearranging it so the e to the x squared is multiplying first, then we can see this as being, well, if we rearrange the du dx, multiply both sides by dx, we get 2x dx. That means this is the same. So we can say, well, this is really just du. So this is equal to e to the u, because u is equal to x squared, times just du. So the integral then, well, is e to the u plus c. Going back to x squared, in place of u, we get e to the x squared plus c. And that would be our final answer. Alternatively, instead of rearranging to get 2x dx, saying that that's equal to du, we could have said that du over 2x is equal to dx. And then taken our integral, I'll just kind of box it off here, and said, well, our integral of 2x e to the x squared dx becomes the integral of 2x e to the u times du over 2x, and then canceled out the 2x to leave us with the integral of e to the u du. And then we would just go to this next step. So that's an alternate way of looking at it. Some mathematicians would not enjoy that approach, but for me, I'm okay with that approach or the previous one. So let's look at another example. So now let's look at the integral of 6x squared plus 4x times e to the x cubed plus x squared. So this is a bit more complicated because now we have two terms out in front multiplying, the 6x squared plus 4x, and we also have two x terms in our exponent, the x cubed plus x squared. But it's still an exponential integral, so we're still going to want to use that same kind of approach of trying to get to a point where we can use our rule, the rule of e to the u du equals e to the u plus c. So we're going to let u equal our exponent, just like we have before, and then we're going to take the derivative of that exponent. So take the derivative of u, so we get du dx is equal to 3x squared plus 2x. And then rearrange for du. So we have du then equals 3x squared plus 2x in brackets, because they're both now multiplying dx. Now what we need to do is deal with that 6x squared plus 4x that's sitting out in front. So if we use the first approach that I used in the previous example, we could say, well, this is e to the x cubed plus x squared times 6x squared plus 4x dx. But the problem is that doesn't match up with our du. Our du is 3x squared plus 2x dx. This is 6x squared plus 4x dx. So we need to do something to account for that. And we can approach this in a couple of ways. One way is to notice that 6x squared is just 2 times 3x squared, and so is 4x. So this is really just this multiplied by 2. So if we multiply our du by 2, we get 2 times 3x squared plus 2x dx. So then 2 du is equal to 6x squared plus 4x dx. So this 6x squared plus 4x dx is really equal to 2 du. So we could make that substitution. Another way that we could approach this is to say, well, 6x squared plus 4x, 6x squared and 4x, they're both multiples of 2, so we could also factor out a 2 from there. So change this into the integral of e to the x cubed plus x squared times, factoring out that 2 times 3x squared plus 2x dx. And either way, we're making that same substitution. We can either say that the 6x squared plus 4x dx is equal to 2 du, so making this substitution, or we can say 3x squared plus 2x dx is equal to du, in which case we have this 2 times this du, so we end up with the exact same thing. We end up with the integral of e, and making the substitution for our exponent, e to the u, times 2 times du. So no matter which way we approach it, we end up at the same place. We end up with e to the u times 2 du. And then again, we can take that 2 out in front as a constant multiplier. So we have 2 times the integral of e to the u du. And now we can use our rule, which says, well, this is really just 2 times e to the u plus c. And then going back to our x form for u, we have 2 times e to the x cubed plus x squared plus c, and that would be our final answer.